Sí. Bien, buenos días a todos. Vamos a empezar este acto, que es una conferencia que impartirá el doctor Jut Wynne. Jut Wynne es doctor en ciencias biológicas, especializado en ecología de ambientes extremos. Trabaja en la Universidad de Arizona del Norte, en Estados Unidos, como profesor investigador asistente, y su carrera profesional es muy extensa y sobre todo muy interesante. Es uno de los científicos que no se conforma con trabajar en los despachos ni en los laboratorios, sino que va a los sitios, va realmente a buscar la información allí donde la hay, y en este caso en sitios muy complicados. Ha trabajado en las selvas de Belice, en las calderas volcánicas de Hawái, en las cuevas de lava de la isla de Pascua, en los desiertos de Atacama, en el Mojave, por citar solo algunos de los lugares en los que ha desarrollado sus investigaciones. Además de ser un habilitado científico, como vamos a ver ahora, y sobre todo como demuestran sus publicaciones, que son muchas y muy interesantes, es un consumado también explorador, y algunas de sus expediciones han estado financiadas por la NASA, la Sociedad Geológica Americana, el Servicio Geológico de los Estados Unidos de América y otras instituciones. Ha publicado también muchos artículos de divulgación y sus hallazgos han dado lugar a un gran número de noticias en la prensa en diferentes países. Hoy el doctor Wynne va a impartir aquí, en la Fundación Gómez Pardo, a la cual agradezco que nos ceda, como siempre, el salón de actos para este acto, por invitación del Instituto Geológico y Minero de España, una conferencia sobre un tema realmente apasionante, que es ni más ni menos la detección de cuevas en la Tierra y en Marte. De sus experiencias, llevadas a cabo fundamentalmente en algunos desiertos terrestres, en cuanto a detección de cavidades mediante algunos sistemas in situ y remotos, se desprenden interesantes consecuencias que pueden ser muy aplicables a la detección, a la exploración y a la investigación de cavidades en otros cuerpos del sistema solar, entre otros pues la Luna y Marte, además de otros satélites y planetas. Quiero agradecer al doctor Jut Wynne su disposición para venir al Instituto Geológico y Minero durante unos días para impartir esa conferencia y también para estrechar la colaboración con algunos investigadores del Instituto, liderados y coordinados por el doctor Eulogio Pardo, que ha sido el que ha impulsado esta colaboración y la visita del doctor Wynne. Esa colaboración se centra en algunos proyectos que se han llevado a cabo recientemente, financiados por el Plan Nacional de Investigación Español, y que otros proyectos que están sometidos a evaluación en estos momentos y que posiblemente posibilitarán el que se estrechen esos lazos de colaboración entre el doctor Wynne y los investigadores del Instituto Geológico y Minero de España. Muchas gracias, Jut, y la dejo con él.
Muchas gracias. Y lo siento mucho, pero es necesario para mí usar inglés. I have a story why it is important for me to use English. I have not been thinking in Spanish much, only 2 days. And when I was in Chile, I had a talk at Universidad de los Andes in Santiago. And I was off the plane. The next day I gave a talk, and I tried to speak in Spanish. My friend who coordinated the talk for me interrupted and said, "Jut, you can speak in English." The entire auditorium started clapping. 2 weeks later, I had to give a talk in Isla de Pascua, and I told my friends at the museum, I think I should speak in English and have you translate because my Spanish is very bad. Well, I had been speaking in Spanish for 2 weeks with my friends that I was working on the project with, and I gave the talk without any problems. And he came to me afterwards and said, "That was a great presentation. You spoke very well in Spanish." So, necesito más tiempo para mi mente a pensar en español. Entonces, lo siento. When we think the exploration of other planetary bodies, Mars, the Moon, we immediately think of this picture, at least I do. This is of Buzz Aldrin looking at the American flag. Buzz Aldrin and Neil Armstrong were the first humans to walk on the moon. Since the Apollo missions, it has been over 40 years since humans have explored another planetary body other than Earth. And for me, that is perhaps one of the reasons why it is very important for us to look for caves on Mars. Because ultimately, when we go to Mars, and when we are able to establish a temporary or a permanent colony on Mars, we will need to live underground. We will be cavemen and cavewomen all over again. The reason why this is necessary is because the surface of Mars experiences cosmic radiation, extreme fluctuations in temperature. The temperature is very cold during the night. And there's also extreme windstorms, which make a lot of dust. And as a result, this can cause problems for equipment. So working underground, living underground is going to be necessary. This is an artist's concept of what it might look like when we live in caves on Mars. Another reason why this is very important is because of the possibility of finding significant, large deposits of water ice. One, we will need water ice for drinking. We will need it for consumption. Also, we can take the H2O molecule, separate it, and we can use the hydrogen for making fuel, possibly for a return trip to Earth. And we will also be able to use the oxygen for breathing. Another very important reason to explore caves on Mars is to answer a centuries-old question, well, perhaps decades old. Does life exist elsewhere in our solar system? Now, I don't expect that we're going to find higher life forms in caves on Mars, but if life existed or exists on Mars, that evidence will be found underground. Now, this might sound like science fiction and like this is not going to happen anytime soon, but NASA has other plans. This is the Space Launch System. This is what I call Apollo on steroids. This is a spacecraft that NASA has announced will take humans to Mars. NASA Administrator Charles Bolden made this announcement, and they say that we will be going to Mars, humans will go to Mars sometime in the 2030s. That is just 15 years from now. However, I think in my opinion, it's not just going to be NASA. The private company, SpaceX, has been making significant contributions to space exploration thus far and have really shown to be an impressive contender for getting us to Mars. Right now, SpaceX and Boeing hold the two contracts for taking equipment to the space station and back. SpaceX has the only spacecraft that actually returns to Earth so that the equipment so that it is reusable spacecraft, whereas Boeing's spacecraft burns up on re-entry through Earth's atmosphere. And I think what will considerably make SpaceX even more competitive and have us look at them even more seriously is this. Today, somewhere off the coast of the US, in the Atlantic Ocean, SpaceX will make their second attempt to land a rocket booster on a drone ship. And they made the first attempt. I'm not sure how many of you are familiar, but the rocket booster exploded when it landed on the platform. They're trying it again. And when this happens, I think that we will start to say, oh, okay, SpaceX, this organization is an organization that will possibly get us to Mars. Astrobiology is the study of basically using Earth analogs to predict what life on other planets might be like. This is a growing, it's been around for a few decades, but it's a growing discipline. And the way in which we identify extraterrestrial analogs is they're close approximations here on Earth to what we might expect to find on another planet. Because unfortunately, we cannot get in our spaceship and go to Venus, go to Mars, go to the moon to conduct our experiments. We have to do those experiments here. And using Mars as an example, when we think about a Mars analog, well, first, as we all know, as scientists, that it's going to be driven by our research question. What are we trying to ask? What question would we like to have answered? And then there are several criteria with which we can identify those conditions for a Mars analog here on Earth. First, wide temperature fluctuations during day and night. High ultraviolet radiation is another criterion. And we would, if we're asking planetary science questions, we want them to be geologically similar. With Mars, Mars is very dry, so we're looking for dry environments. And it's very important to recognize that rarely are all of these conditions met. So it circles back around to the research question. It goes back up to what are we trying to ask? What question would we like answered? And that will enable us to determine whether or not we can relax some of those criteria. So for example, maybe it being geologically similar isn't as important. We were studying caves in the Atacama Desert of northern Chile. These are salt caves, and we don't know of any salt caves on Mars, but because all of the other conditions were met, we identified this as being a good Mars analog. Concerning life on Mars, there's actually a few criteria that we use, but one is called the habitable zone. And calculations were made by Frank and others in 2001, and they came up with 3 estimates for habitability of a planet. And basically this was distance from a star to where the planet was occurred. The first, and which is most conservative, is between 88 to 127 million miles from the sun. The second is this intermediate level, 78 to 164 million miles from the sun. And finally, the least conservative was 90 to 177 million miles. And when we think about habitability of Mars, well, we know that it's between 128 to 155 million miles from our sun, which falls into that intermediate zone. So with that in mind, okay, that is met. So life might exist based on just where Mars is positioned within our solar system. We know from life on Earth that water is required for life. And we also know that a few billion years ago that Mars was once a very wet planet. Today, as we know, it's a very dry place. Or is it? This study was released yesterday. They found water just beneath the surface in Gale's crater on Mars. And Gale's crater is located just south of the equator. So we know there's water at the poles, water ice at the poles of Mars. We're finding liquid water just below the surface, south of the equator, which is now beginning to suggest that maybe there is a lot more water underneath the surface than we had previously thought. Some colleagues of mine in 2010 published a paper modeling where it was likely for water ice to occur within caves. And their predictions are here in red. Those are the areas where it was most likely for there to be stable water ice. As I mentioned earlier, water ice will be important for astronaut missions to Mars and might also be important for looking for life, selecting those caves which would be most likely to support evidence of life. And regarding Mars analogs, as I mentioned, I don't think we're going to find little green men. I don't think we're going to find large-bodied animals in caves on Mars. It will most likely be in the form of microbes. This is an example. This is a eukaryotic algae from a cave in northern Chile. These are examples of sulfur oxidizing bacteria. These bacteria are actually eating the sulfur. This is another example from Cueva de Villaluz in Tabasco, Mexico. And these are called biovermiculations, and these are also believed to be oxidizing the sulfur. They're actually eating the sulfur. But perhaps one of our best examples for the type of microbes we might expect to find on Mars, if life ever evolved there, are these features. These white features that you see in the slide are called corrosion residues. And they could be, we weren't able to confirm this, but these could be the corrosion residues associated with rock-eating bacteria, which we know on Mars there's a lot of rock, so this type of situation might indeed be possible. So looking at cave detection, the working hypothesis was this. We were looking for temperature differences, the maximum temperature differences between the surface of the ground and the entrance of the cave. And we based this upon our understanding of how the temperatures of caves and the surface behave and interact. For example, the deepest part of the cave, the temperature of the deepest part of the cave represents the average annual surface temperature. The surface, we know, when the sun rises and sets, it heats up the ground, so the ground temperature changes with the rising and setting of the sun. It changes diurnally. And we know that the entrance of the cave is a combination of the deepest part of the cave and the surface, the ground surface. So once again, what we're looking for is we're looking for where the differences are maximized between the entrance and the deepest part of the cave. And the way in which we did this was we wanted to basically collect as much information as we could from caves using temperature instruments. And you can see here, this is a diagram of a cave, and we placed these instruments throughout the length of the cave. We also placed instruments on the surface around the entrances, and this was enabling us to begin to model the differences between internal cave temperature, the entrances, and the surrounding surface. And here's some of our results. This was from a paper published in 2008, and you can see here, in blue, we have the surface, o superficie, the entrances, entradas aquí, and what we are seeing is we see almost a 20 degrees Celsius difference between the entrance and the surface, indicating that we could detect this cave using remote sensing imagery, in the thermal in particular. This is another example where we saw the same pattern. You can see once again almost 20 degrees Celsius difference between the entrance and the surface. We also wanted to understand how temperature was changing throughout the length of the cave and how that might influence what was happening in the cave entrance. And the way that we did this, oh my goodness, lo siento mucho, this is a very bad slide. Is there a way to dim the lights in el frente? Okay, perfecto, gracias. These are three-dimensional maps of Cueva Mina Chulacao in the Atacama Desert in northern Chile. And so we took the three-dimensional maps, we took the locations of the instruments, and this is a simulation of looking at temperature differences of the entrance and seeing how that can be different from deeper into the cave. And this is what we will ultimately be modeling when we combine the data from the temperature data that we collected from the caves with the three-dimensional data of the cave. Turning our focus to the detection of caves here on Earth, when we first wanted to demonstrate, to show that this concept was possible, we took a thermal imaging camera and stood in front of the entrance of a cave and took photographs. And we did that, we divided the day, the 24-hour day, into 4 periods. We have the afternoon, late afternoon, in the morning, this is mid-afternoon, and this is early afternoon. And you can see, este tiempo es más mejor para la detección de las cuevas y eso aquí no está bien. And we see similar patterns when we looked at other caves. And it's the same pattern. We then had the opportunity to take a camera that was developed by NASA Goddard, and we put this on top of a volcano, and we looked down onto where the caves were on the lava flow below. And we have here, this is a tunnel. This is not a cave, but is similar to a cave. And this feature here is an actual cave. We collected images every 10 minutes for 24 hours, which gave us 122 images. And we then used a principal component analysis to basically look for dimensionality in the data, or to reduce the dimensionality in the data, rather. And we were able to see that we had, when we ran PCA coordinate 3 and 2, we were able to see that there is separation from the feature that is not a cave in comparison to the actual cave feature. So we were able to detect differences using a lot of data. We also took controls from several pixels that were not caves, just on the ground surface, and those are represented here. And once again, we saw separation between what is a cave, or what is a cave here, and what is just the ground surface. We then conducted another experiment where we collected data every 10 minutes for 24 hours of one cave in the Mojave Desert. And you can see here where the temperatures between these entrance and the surface change. You can see the entrance becoming dark, indicating that it is during the day, and light indicating that it is night, which is depicted here as well. And we see that same pattern that we saw when we collected the images in our earlier work in 2006. So everything is lining up as far as showing that the best time is early morning, a time that is probably not so good as during the late afternoon. And the reason why this time is not good is because we were concerned that because this is very bright and it's hot, that the hot ground around the cave entrance might be strong enough to cover up the signature of the cave. So we might not be able to see it. As our work progressed, we were able to conduct 3 different missions. We conducted one mission in a hot air balloon platform by looking down at the same area. And then we conducted 2 missions on board this aircraft here in April of 2011. And we collected data during the middle of the day, which was a time when we thought we would not be able to see caves, and before dawn, which is the time we thought we would be able to see caves. What we found is when we took the data from the earlier image that I showed you, the principal component analysis, we were able to, when we were looking at determining when the best detection times were going to be, the data demonstrated this as well. Pre-dawn was the best, and there was this very small window during the day when we could possibly detect caves between 13 and 1400 hours. With our hot air balloon platform, we wanted to see when the best time, when we could, this was part of a baseline effort, this was part of an early study, and we were collecting data before sunrise. And then we also returned in the middle of the summer when it was 30 degrees Celsius during the day, well on average during the month of July. And we wanted to see if you could actually find caves using thermal when the ground surface was much hotter than it was in late March. So I want to provide this for reference when we're looking at these next images. This is the tunnel feature up here. These are the results of the hot air balloon mission that was flown by NASA. What you can see in this image is we found 4 of the 5 known cave features. That tunnel was also detected. And then when we were examining the data collected in July, when it was very, very hot, we were still able to see some of the caves. We found 3 of them. One of them was difficult to see right there. And we were still able to find or see that tunnel feature. We conducted this aircraft mission in 2011 in April, and we had to take, this was basically the approach that we used. We established these tie points, which is very similar to what Logo and his colleagues are doing in southern Spain. And when we flew the aircraft, we basically had to fly the aircraft like this to collect the data. And one of the problems that we encountered, and you can see it in this next image, is that when the aircraft is collecting imagery, the winds will force it to do this. And you can see this is the result. The images that are collected in sequence are not collected in a straight line, and that makes the challenge for georeferencing, or what we call rectifying the data, a little more challenging. But we were able to do it. This is one of our tie points, and you can see here that we were able to find one of our known caves from the imagery that we collected from the aircraft. And now for Mars. In 2007, I was a co-author on a paper identifying 7 very large vertical shafts on the Martian surface. These are all on the northern flank of RC Mons. These are the images, or these are the actual collapse pits or vertical shafts from that work. And to get an idea of scale, this is a football field, 90 meters in length. And this feature is 100 meters across, so it's slightly larger, or slightly smaller than a football field. This is also an interesting result. When we were looking at detection times for Mars, now this is the Themis imagery here, and this is from Mars. We found that midday was a very bad time for finding caves. This is that feature here. You can barely see it, and if you were looking at a very large image and trying to find a cave within it, it would not be possible. This was collected at 1500 hours. This here, you can see the cave very well, and it was collected before sunrise at 0400 hours. Our next question from the terms, or from the perspective of exploration, both for robotics and for human habitation, is this a cave? Is this actually a cave, or is this just a deep vertical pit? Well, we used what is called the HiRISE spacecraft, which is a high-resolution orbiting platform that captures data basically captures photographs, red, blue, green. And it has the ability, when it's looking down at Mars, it can rotate like this. We call it, in English, it's pitch and yaw. And so it was able to look at an angle into the pit. And we can see, here's the rim or the lip, and we can see that it goes in just a little bit here. We don't know if it extends in this direction or if it extends in this direction, but we do know from features in Hawaii that there are often caves associated with these types of features. Today, there are over 2,000 cave-like features identified on the Martian surface. Glenn Cushing with the U.S. Geological Survey has been developing a database on these features, and these are now the features that we are looking at for identifying how we should move forward with future missions involving the ultimate exploration of caves on the surface of Mars. Also interesting, because we recently had 2 platforms that were collecting high-resolution images of the moon. These look very similar to what we're seeing on Mars. They are similar features, and today researchers have identified over 200 cave-like features on the lunar surface. So to sum things up, in conclusion, detectability of caves, both on Earth and on other planetary bodies, is going to be determined by how the cave is shaped, the structure of the cave, and also the surface topography. But also, most importantly, is going to be determined by how we can see the cave from the surface, or from a remotely sensed platform looking down at the surface. If we're only able to look straight down to the ground, it could be challenging. More challenging, if we have the ability to look at an angle, we might be able to see more. Also, and this will depend once again on our research question, we will need to be able to see the differences between what is a cave, or what is a tunnel, or what is a shallow cave, or that maybe goes back 10 meters. And the reason why this will be important, once again, this will be question driven. If it is for an astronaut base, a shallow cave may be appropriate. If we're looking for evidence of life, we may want to select the deeper caves. As I mentioned earlier, alternator scanners that are looking at an angle will be important for finding more caves on both the Moon and Mars. And what we have identified thus far, as far as these features that we know, the 2,000 features on the Martian surface, the 200 features on the lunar surface, these are now our primary targets. These are the sites that we will be looking at for future exploration. And wanting to see where this work is, the current directions of this work, what we are currently doing right now for this study is the work that we conducted in 2011, the 2 aircraft missions that we flew We collected over 7,000 images, thermal images, and we are now analyzing those images. Also, those 2,000 features on the Martian surface. This is that map of Mars once again. These are the areas where water ice might occur. We are in the process of identifying all the features that are going to be within these areas where water ice may occur within those caves. And then we're going to basically start to scale down that data set from 2,000 caves to a lower number of caves, which we're using a selection criteria for identifying the caves for future robotics missions, future human habitation, those caves that are most likely to contain water ice. So we're going to start to basically identify the caves on Mars that we should be looking at when we ultimately send robots to investigate caves on Mars and ultimately humans. I'm also working with spacesuit designers to develop a group to develop tools so that we can work underground efficiently and safely. Right now, there are no tools available for working on Mars, specifically using mechanical and motorized ascenders and descenders, equipment for climbing up and down cliffs or going in and out of caves. And we are also testing improvements in spacesuit designs, padding for the elbows, padding for the knees, better gloves, so that we can be able to work underground safely and efficiently. Also, as was mentioned earlier, in Parque Nacional Sierra de las Nieves, I am working with your colleagues here, Uloco and others, to conduct a study similar to the one that we were conducting in the Atacama Desert of northern Chile and in the Mojave Desert. And our objectives will be to use a Zeppelin, a hot air balloon, to collect thermal imagery of this region and also to collect ground temperature measurements from the surface and inside the caves. And now, once again, getting us to Mars. What do we need to go to Mars? Because, as you recall, NASA said that we're going to be sending humans to Mars in the next 15 years. Well, first, as I mentioned, we need to know, because we will be living most likely either temporarily or permanently underground because of the very difficult surface conditions. This is me working with NASA JPL engineers testing the world's first rock climbing robot. This is Lemur. This is us climbing into a cave using the robot. This robot is in the very early stages of development. Right now you can see all of the cables associated with the robot. This is for the computer. This is for power. There is no power supply. There is no brain or computer on the actual robot. So the JPL engineers are working on this to develop autonomy to where this robot can go into a cave and make decisions about moving through the cave. Because right now, the computer has to tell the robot how to do everything. And you can see here, this is me featured down here. I'm having to hold the robot because if it fell from here, from the rock, it would crash to the ground, and I'm preventing that from happening. So a lot more work needs to be done with this technology before we can look for life in caves on Mars. Also, a lot more work needs to be done in terms of spacesuit design and development for working in caves on Mars. And that is something that we're going to be working on in the coming months, within the next few months. And we will ultimately be developing a proposal to do this work, hopefully through a NASA contract. And human habitation. This is an artist's concept of what it might look like one day to live in a cave on Mars. Colleagues of mine at University of North Dakota, are developing inflatable habitats that we can insert into a cave, inflate, and then humans can live underground. But this technology is in a very early stage, a very early part of development. So a lot more work needs to be done here as well. There are many, many people that we have to thank for this work. I'm sitting here by myself speaking, but there have been over 30, 40 people who have assisted in this project over the years, and it is to them that I owe a fond appreciation, because without them, this project would not be possible. Muchas gracias para su atención, and if you have any questions, I would be more than happy to answer them now. Thank you. Thank you so much for your time.
¿Hay alguna pregunta? ¿Nadie se anima a ir a Marte?
Yo tengo una pregunta, pero no para ir a Marte.
Pues
Cuando has mostrado en Spanish, o en inglés mejor, en inglés.
Sí, sí. Es más fácil para mí, lo siento.
In the results of the principal component analysis, it seems that there's a different behavior between the tunnel, no, and the natural cave.
Yes.
That is based on sequences of the same, or photographs of the same place taken in. So is the dynamics what makes the difference, or the average mean temperature of the different entrances?
We had 122. Would you like to translate the question to Spanish first, and then I can answer you, and then you?
No, I think